Hi everyone, this is the Makers Machining Flange team. We've spent a couple of episodes talking about machining this flange. The first one we did was about a week ago. I just told about how we did internal threading, and then a couple days later we actually had our camera inside the machine here while we machined this. But this is kind of an unusual piece that not everybody uses or sees every day. So we're going to talk a little bit about the planning of making this part here. It depends on how many you're going to make, determines how you're going to do it or what. We were making 300 pieces, so we made a fixture to quickly put them in and out of the fixture. But if you're going to make one, and you know, it's an unusual part, you might look at, I need to get the blank made. How am I going to do all this? We were talking during the process here, if we're going to just make one or two pieces, we'd probably get a round piece of material, which this thing here, I believe, according to the print, is 7 1/4 inches on the outside. So if you had a 7 1/4 inch diameter piece of material, it's 1/2 inch thick, you could put that in the lathe, bore the hole, cut the threads in there, then you could take it out and maybe lay it out on the plate and saw it, belt sand it to get it smooth a little bit, and then do your turning and threading, and then you'd have to know where your tapped holes are going to be to put in there.
And all that depends on the customer's specifications, on what they need.
First of all, you got to find out, what am I making this out of? Am I making it out of plastic, steel, aluminum, stainless steel? If you don't make it out of the right material, you've wasted your time. In this particular case, we had quite a few of them to make, and we bought these as plasma cut burnouts. It's A36 steel. It's a low carbon material, but it's a good steel that's commonly used. And we had these plasma cut, so they all come out exactly the same as we talked the other day. There's a little bit of a lump out there. It's always in the same spot because they make the same cuts. So we got enough quantity to justify having the things plasma cut. Now, again, back to the quantity affects the way you do it, and also the price of what it would cost. Now these burnouts here, 1/2 inch plate, they cut the shape and rough a hole in there. You do 300 of these, we got burnouts for 10 bucks a piece. Okay, you couldn't touch the big disc for 10 bucks, or if you bought a flat plate and did all your layout, you couldn't even start at 10 bucks. I had the whole thing burned out for 10 bucks, and the only thing we worked on was the bore and the threads and tapping the two holes. Everything else was done.
But if you called that place to burn you out one piece, it wouldn't be $10.
No, there's probably a $100 minimum to burn one or 5. You could probably get 5 for the same price as one, but it's still going to cost you 100 bucks. But anyhow, so the thinking process was, how are we going to work on this? Obviously, we knew that we were going to buy a burnout and work it from there. So then I'm going to let Joe take over here a little bit. If you want to come on in here with the camera, we made this fixture. You saw it the other day while I was in the machine machining the parts, but why don't you take it from here, Joe, and you can show what we did to make that fixture there.
Well, first thing I noticed on these pieces were being flame cut or plasma cut, they are still in pretty good condition, you know, except for this little bump here, but I grabbed a small sample and noticed that they were all in the same spot, so I figured I could just maybe mill a notch on my fixture to accommodate that, and it worked out pretty good.
We made the fixture so we could take this fixture and put it in any machine, and as we mentioned the other day, we machined a flat on there which is parallel with where the two tapped holes are. So all we have to do is orient that thing in the chuck, pick up that flat, and we know where we're going to be locating the fixture. We had talked about maybe making some jaws and machining a pocket in the jaws to fit that part, but then you've got to use the same jaws every time you do the job, and not all jaws fit in all machines. So
all our lathes use different jaws, so if we were to marry a set of jaws to this job, it would be, we'd have to do it in the same machine, and you know, typically sometimes that'll work out, sometimes it won't.
Another issue that we were concerned with was this burnout here has got a fairly thin wall here, so if we were going to grab this in a chuck, a 3-jaw chuck with jaws made to fit, or a 4-jaw chuck, you'd fight this thing forever trying to do this job in a 4-jaw chuck because it takes time to locate it. So our concern was not to squeeze this thing, because when you machine it, thread it, and then you release the chuck, you wouldn't have your right size. So this fixture plate here holds that burnout down in place, and we get clamps on here, and that clamps it flat to a surface. There's no outside pressure to clamp and hold that thing in the chuck. You want to talk about this nice little feature here, Joe?
Yeah, so I ran quite a few of these, and it wasn't really an issue, but obviously time is of the essence. We want to get these in and out as quickly as possible. So what I was noticing was I kept fighting with these clamps to get them out of the way. So unscrew that.
It's a tight screw in there. So he's going to take it apart there. You can just tell what you got in there. He's got a little spring underneath there, and so as soon as you take the pressure off, the spring lifts up the clamp, and you don't have to worry about the thing spinning out of position.
So a little piece of spring under there will keep it in place enough to
holds everything right there.
Just right there, and it's nice.
Easy to crank that thing tight, and then you can run your whole process in there, machine it, and you're done when it comes out. Yep. The machining that we were doing there, like I said, we tapped these holes while it was in the lathe, and in this lathe we've got these attachments that go in and allow us to either cut a keyway in a shaft, which is, you know, the end mill or the cutter is aiming towards you, or you've got these other fixtures that hold taps, drills, taps, or countersinks going towards the chuck, so you can do these tap holes. You know, Joe had to figure out where can we put these clamps so we don't interfere with where the tooling comes in to tap that hole.
Yeah, that was another thing. I put these clamps so they could swing. You know, you got a generous amount here where you could clamp it pretty much anywhere. It's not going to affect anything, and it's not by accident. That's all figured out ahead of time. Then
you don't have to worry about the drill or the body drill ever hitting.
Even the chamfer on this ID thread. You know, there's no way that tool is going to hit these clamps. So
short enough to miss everything that could be interfered with. The only thing you got to worry about is after you've drilled your hole, you need to retract far enough so the chuck can index around and drill the other hole without the drill getting hit by the clamp there. That's the only thing you have to worry about.
And that's just a matter of a little programming.
Yeah. Now here we got some of our threading inserts here. You can see the little threading tools here that we use. These are really nice because they'll have an insert that's made to the specific thread size that you're cutting, and when you get down to the bottom of your cut, it actually breaks the sharp edges off the threads. It's really, they've got these inserts, there's so many different sizes. They've really done a nice job with creating inserts that give you a quality part in many ways. So
yeah, when we started out, we used a universal insert. We were fighting the burrs.
Yeah.
And then I ordered some pitch specific inserts, and they worked really good. Yeah, really well.
Anyhow, we got to do a little figuring. There's a lot of math involved with figuring out what size hole you put in there. Where'd you find that out? What size do you have to bore this for the right size? 4-inch, 8 threads per inch NPSM, I believe it is.
Yeah, I googled 4-inch NPSM specifications, and I was able to acquire all the info I needed. So
this has 8 threads per inch, and if you look at your decimal equivalent chart here, it gives you some of the pipe tap sizes here. And pipe threads, you know, there's like 27, 18, 14 threads per inch, and then they get to 11.5 threads per inch. What a weird number. I don't know where they came up with that. And that's for about 4 or 5 sizes, and then they all go to 8 threads per inch after that. Maybe there's coarser threads if they get into real big pipes there, but 8 threads per inch. I want to say too, you know, we got a 4-inch pipe thread here, or a thread on a 4-inch NPSM pipe. Typically, a pipe is rated where the inside of the pipe is the 4 inches, and then whatever your wall thickness is, that's where the threads go on the outside, for example. So this thing may screw into have a 4-inch pipe that threads into it, but the burnout that I bought, I got a 4-inch hole, so I knew I was going to have plenty of stock to machine away to get a nice true diameter to get the thread cut in there. So anyhow, here's your thread chart. It tells you what size to use. This case may have been a little bit different. A 4-inch 8 thread, which is basically what this was. You have to have a 4 1/4 inch hole. So that bears that out, right, what I just said. The thread size is going to be bigger than 4 inches because the idea of the pipe is 4 inches roughly.
The minor diameter turned out to be 4.340, I think. Was the through one? Yeah.
Okay. That sounds about right. And if you're ever questioning if you get some weird part that you have to make 8 threads per inch on something that's not a 1-inch 8, on this decimal equivalent chart there's only one thread here that's got 8 threads per inch. It's a 1-inch 8. But let's say you were working on a 100-year-old steam engine and they put a 1.25 inch 8 thread in there. Dan's smiling back there behind the camera because he's probably seen a few of those. If you have an 1.25 inch 8, you can say, okay, well, what tap size or what tap drill size do I use for a 1-inch 8 thread? You move over here, 7/8. So a 1-inch 8 thread is going to need a 7/8 inch hole. So conversely, if you had an 1.25 inch 8 thread, you'd have to drill an 1 1/8 hole. So it's be 1/8 of an inch smaller for your threads to cut and finish properly.
The thread height's going to be the same no matter what diameter the thread is.
Exactly
the pitch, whatever the pitch is, that thread height's going to be the same across the board.
8 threads per inch. How far apart is each thread?
1/8 inch.
1/8 of an inch. 8 into 1 inch is 1/8, right? Or 8/8 of an inch. So if you got 16 threads per inch, it's a 1/16 of an inch between threads. Those are about the 2 easy ones that work out.
Yeah.
20 threads per inch, or how far apart?
50 thousandths.
50 thousandths, exactly right. So, anyhow, a little math.
13 threads per inch, or how far apart?
Don't ask me.
83 thousandths.
83 thousandths.
Wait, no. Oh man, it just was 76 thousandths or 77 thousandths.
When you do it all the time, you kind of remember that, because in these lathes, you usually program in the distance between the teeth, not how many threads per inch. They don't ask you that.
Yeah.
So. How much time we got on that thing there, Dan? What's the clock say? 3 minutes? Okay. All that information, talking about conversational controls. This is not conversational control like other simpler machines, but this thing can work a lot faster and do better work than the simpler machines. They might have conversational controls, but they might ask you some prescribed questions as to what parameters to put in. So anyhow, this thing worked out. Tom got this job done in no time flat.
Yeah.
We had 300 pieces, and what did it take? About 5 minutes a piece or something like that? 3.5 of machining time. By the time you take the part in and out of the fixture,
probably about 5
it takes
minutes.
a little bit longer. But working together to get all these jobs cranked out here, you want to be expedient as possible, and
in doing so, hopefully you get the job again. We have a nice fixture here where plop it in any machine and be able to do it.
We've got a lot of fixtures sitting around here.
That's right.
We may not use them all very often, but when the time comes, we've got it. So anyhow, I guess that's all we got for today. This is the last chapter on this flange. You won't hear any more about it. If you have any questions, or anytime you hear me or any of us misstating something, call us out on it. I noticed a few times going back over some of the videos that I said something that wasn't quite accurate, and I need to hear from you if you notice that. Maybe I do it on purpose, and I'm trying to see if anybody's listening. Possible. Anyhow, we'll be moving on to another project after this now, and keep watching. We'll see you soon. So long.